I'm here now with my colleague Reinhard. Thank you for joining.
Yeah, great to be here. Good morning,
Yeah.
Oliver.
And the topic now is fuel cell and electrolyzer. Yeah, this is a more and more growing important topic because of the hydrogen industry. And we are not only focusing anymore on automotive, but a lot in the meantime also on industrial and energy generation application fields. And the more this topic becomes important and widespread, the usability, efficiency of workflow and modeling has a stronger impact. So what is new with a modeling setup?
Yeah, we have spent a lot of effort in streamlining the workflows, and especially to support the activities in industrial green energy with solid oxide fuel cell and electrolyzer systems. We have now available in CRUISE M a solid oxide system generator that supports the user in setting up entire system models very efficiently. And yeah, I would say let's have a look how this generator works. Yeah? So the user simply starts the GUI and then selects from the different generators and wizards the solid oxide fuel cell and electrolyzer wizard, and then in its simplest form, it's only required to enter the active cell area and the number of cells in the stacks, and based on this information, the generator automatically sets up, in this case, a solid oxide fuel cell system model with all the different components and subsystems comprising the thermal network, the electrical network, the gas flow network. And it's the components and subsystems, they are pre-specified and already configured and sized to fit to the stack power level. And based on this basic parameterization, the model is ready to run. But the user, if he wants to, he can step into each component and can adapt the parameterization, can select the different reaction mechanisms, can modify the type of fuel used, whether it's methane or whether it's ethanol. Especially in this afterburner component, he can select among different mechanisms for the reactions, and yeah, so parameter studies are made easy with this system generator, and very, let's say, and also enables new users to quickly get familiarized with this topic and this system configurations, mechanizations, and
yeah. When you set up the models, is it also required to have some measurement data to set up the model, or can you do it from scratch?
Well, we have some generic stack data in the background, so it's possible to really start off from scratch. And whenever experimental data are available for either the stack or other components, these data can be used to refine the models and to adopt them to the specific configuration under consideration.
Yeah, this is very impressive from the setup, how easy this is possible. When the model is set up on the simulation side, is there anything new also from the implementation in the kernel?
Yes, we've done a lot of let's say improvement and extensions, refinements, and a specific highlight in that context is our chemical equilibrium calculator that is applicable as a additional new component and also available in the quasi-dimensional pipe, in the plenum component, in the stack component, and enables a highly efficient calculation of the species composition related to a specific temperature, pressure, stoichiometry situation, and so it's very handy for the user to either use the classical time step based integration of the chemical kinetic reaction mechanism, or to use this chemical equilibrium approach, which is applicable, as I said, to various components.
So it means it's easy also to have fast running models which are then able to run really in a larger series and do parameter studies with.
With this equilibrium approach, yes, you can considerably further speed up the simulations, so that you can run hundreds or thousands of variations of different components and subsystems in a very efficient manner.
Yeah, we talked now a lot about solid oxygen fuel cell, electrolyzer. Of course, important are also a PEM fuel cell. What's new in the area of PEM?
Yes, on the PEM fuel cell side, in the previous release, we had in our multiphysics simulation solution FIRE-M, we have brought the high temperature PEM capabilities, and we have now made this feature also available here on CRUISE M site, to enable the user to fully use the stack and cell modeling capabilities for high temperature PEM applications. So to run these models in the temperature range between 130 and 200 degrees C, and due to its physical based nature of the modeling of the underlying stack reactions, we can again achieve a very high accuracy, and we've done extensive validation of the model and comparison between experimental data and the simulation, and so we are very happy with the degree of accuracy we can achieve, and the model is fully compatible with our PEM fuel cell parameterization wizard. So also here it's very easy for the user and very fast to achieve to have a reliable model based on just a few experimental data.
You mentioned already at the beginning of the high temperature PEM fuel cell, FIRE-M, that this was available in FIRE-M, is now available in CRUISE M. When we step now to FIRE-M, what is there available for the full 3D simulation capabilities with respect to fuel cell electrolyzer?
Yeah, let me start with the fuel cell. So we got a lot of feedback regarding the parameterization from our customer base, and there was a strong wish to make it easy and automated to set up a working model, a reliable model, and we have now implemented the automatic stack model parameterization capability, where the user simply specifies UI curves for a reference operating condition, maybe with different temperature level, different pressure level, different stoichiometry, and the material data of the stack, and all the, let's say, uncertain information, uncertain data like electrical thermal contact resistances, and that might lead to some uncertainty or inaccuracy in the polarization curve modeling, are now automatically adjusted with this automatic parameterization approach. So the resulting model fulfills, with a unique set of model parameters, fulfills the UI curve, or the voltage current relationship for the entire operating parameter space under consideration.
So I understand, similar to initially the generator, also this will help to increase the productivity, to reduce the model setup time for efficiency enhancement.
Absolutely, yes.
Yeah, coming now also here in fire, more to the kernel side. I heard that also here for electrolyzer, there's something new.
Yeah, electrolyzer topics keep us very busy at the moment. So we see a lot of increasing interest and activities in this area. And there are very high, let's say, requirements regarding the achievable accuracy, the predictive accuracy. And it's the liquid water treatment in the electrolyzer that it's decisive for the process, for the overall process efficiency, and for the local transport and conversion phenomena. And so we have spent quite some effort regarding a refined modeling of the liquid and dissolved water processes occurring inside a fuel cell, but mainly inside electrolyzers. And with this refined modeling, we could further improve the accuracy level that is achievable with our PEM electrolyzer and our anion exchange membrane electrolyzer models.
Yeah, it's always impressive to see how the topic of fuel cell electrolyzer is expanding over different technologies and capabilities. Thanks a lot for your time, for this introduction, and thank you for staying with us.
Yeah, thank you, Oliver, for the invitation.